Hello there guys, welcome back to another epic inexorable maths video. In this video we're looking at something called Serret's integral, okay? So Serret is was a mathematician, okay? So Joseph Alfred Serret came up with this integral and it's just kind of a cool problem, it's kind of a fun problem. So what we're going to do is look at this integral and then we're going to look at a slight generalization of it, okay? So we can slightly generalize it, it's kind of interesting and hopefully you enjoy the video, but let's just go straight in and there's not really much I have to say about it, so we can just begin. Okay, so let's just see what happens. So what we're going to do is make a substitution. That's what we're going to start with, okay? So we're going to say, let x equal tan theta. I was just trying to work out which variable I would use, but I'm going to use theta because we're going to have to do another substitution later, so it just makes sense to use theta here. Okay, cool. So if we do that, let's just see what happens. So dx d theta is sec squared theta, okay? And let's rewrite the integral. And by the way, guys, I'm going to call the integral I. Just for now, I'm going to call it I, just so I can easily refer back to it. So I, the integral that we're trying to find, is now going to be equal to the integral. And let's do our limits of integration here. So when x is 0, we've got 0 equals tan theta. That means theta is going to be 0. And then when x is 1, we've got 1 equals tan theta, and that's going to give us pi over 4 for theta. Then we've got the natural log of x is tan theta, so tan theta, and then plus 1, close bracket, divided by tan squared plus 1. Okay, and just a quick remark on this, and actually let me do the dx first and then I'll say that remark. So dx is sec squared d theta. Okay, so we've got sec squared d theta there. Okay, and of course we can cancel some stuff out, we'll do that in a second. Quick remark is you might say, how on earth would anyone think of using x equals tan theta? That's kind of random. But if you remember that the integral of 1 over 1 plus x squared on its own, this is just inverse tan, okay? So this is inverse tan of x. So we have that 1 over x squared plus 1 or 1 over 1 plus x squared. So it doesn't mean that's instantly what you should do, but it's kind of a hint. It's not complete madness, I guess. Now, you might also know that tan squared plus 1 and sec squared are the same thing. Yes, they are the same thing. Okay, it's a trig identity that sec squared equals tan squared plus 1. So we can cancel them out because they are the same thing. Okay, hopefully everyone's pretty happy with that though. So now what we have is that I is the integral from 0 to pi over 4 of the natural log of tan theta plus 1 d theta, okay? Now, what I'm going to do is I'm going to come over here and I'm going to write that down because that's going to come up later, okay? So the integral that we're looking for is the integral from 0 to pi over 4, as well as being the integral that I've actually boxed, and that's what we're looking for. It can also equivalently be written as this integral, okay? So 0 to pi over 4 of the natural log of tan theta plus 1 d theta. Okay, you might say, why are you writing it over here? You will see, okay? This is just something that we're going to leave on the board and we're going to refer back to it, okay? And now we're going to keep doing our working out. You will see. Don't be confused. Don't let me confuse you, okay? So we're going to start from the top of the page and we're going to keep going. And eventually we're going to need this again, right? So at the moment we know that it is equal to the integral from 0 to pi over 4 of the natural log of tan theta plus 1 d theta, okay? Now we've not found what it's equal to, so we need to keep doing working out. So what should we do now? This is a trick that's not immediately obvious either, but if you're in doubt with an integral, one trick that you've always got up your sleeve is to do a substitution that makes you integrate backwards, and I'll tell you exactly what I mean. So we can let a new variable, u, equal pi over 4 minus theta. What this is going to do is it's going to swap the order of integration, or it's going to swap the limits of integration, and then it's going to slightly change the inside of the integral. and it's going to allow us to do a trig identity, which is really, really good. Okay, so just take my word for it that this is going to be epic. Okay, so this is then equal to the integral from. Now, again, when theta is 0, we've got that u is pi over 4. And when theta is pi over 4, we've got that u is 0. So it has swapped the limits there. We've got the natural log of tan, and again, theta, moving stuff around, is pi over 4 minus u, and then plus 1. And d theta, okay, we know that du d theta is minus 1 according to this formula. So d theta is minus du, okay? So we can put a du here, but we've got to put a minus out here. Now, you may or may not know this, but you can in fact put the limits of integration back the right way round as long as you also multiply the integral itself by minus 1. And actually that's really good here, okay? Because what we can do, what I'm saying that we can do, is we can get rid of the minus, but swap the limits of integration. And you can do that, okay? I'm going to write something down for that in a second, but we've got the natural log of tan of pi over 4 minus u plus 1 du, okay? So what I've just done there, just to be clear, is I've said that the integral from, let's say, a to b of f of x dx is equal to minus the integral from b to a of f of x dx. And that is true. That's true, okay? That is true. Another thing that I'm just about to use, so I'm going to write it down, is the compound angle formula, or the addition formula for tan of a minus b. So tan of a minus b, we're going to use this in a second, is equal to tan a minus tan b over 1 plus tan a tan b, okay? So we're going to use this in just a second, and we've used the top one already, okay? That's just a little side note there. Okay, so it's looking kind of okay, and you're going to see something in a second, but remember that thing is in the box up there, okay? So remember, that's still just like lurking because we're about to use it. So continuing the working out, but over here, just to make some more room, we've got the integral from 0 to pi over 4 of the natural log, and then I'm going to use this compound angle formula for tan. So pi over 4 is a, and u is b, okay? So instead of writing tan of pi over 4 minus u, I can write tan of pi over 4 minus tan of u over 1 plus tan of pi over 4 times tan u. And remember, there's still a plus 1 there. So plus 1 du like that, okay? You might be thinking, oh my God, you're making it so much more complicated, but you will see where the magic comes, guys. You will see. Okay, so then we've got the natural log of tan of pi over 4 is the number 1, okay? So it's the number 1. So we can rewrite this as 1 minus tan u over 1 plus, and again, tan of pi over 4, that's 1, so 1 plus 1 times tan u, and we've still got that plus 1, so now we've got this. And if you're an eagle-eyed viewer, you might notice something, but don't worry if you haven't seen it yet, because you'll see it in a second. We can keep going. The integral from 0 to pi over 4 of the natural log, and the number 1, I'm going to rewrite this as 1 plus tan u, so that I can write this all as one big fraction. They have the same denominator. So I've got 1 minus tan u over 1 plus tan u plus 1 plus tan u over 1 plus tan u du like that, and bracket there. Now you really may be able to see what's about to happen. 1 minus tan u plus 1 plus tan u is just the number 2. So this is equal to the integral from 0 to pi over 4 of the natural log of 2 over 1 plus tan u. And I'm going to write it as tan u plus 1. Okay, but they're the same thing, obviously. All right, and now let's do one more line of working out before we restart at the top again. This is equal to the integral from 0 to pi over 4 of the natural log of 2 du minus the integral from 0 to pi over 4 of the natural log of tan u plus 1 du. Okay, just to explain this, I've used a logarithm rule that says that the natural log of a fraction is the natural log of the numerator minus the natural log of the denominator. Okay, and then I've split it into two integrals. Okay, that's all I've done. So it's nothing complicated. I've split it into two integrals, and now we're going to tackle them separately. But now, guys, if you look at the bottom integral there and you look at the top integral there, we've got something that looks pretty much the exact same. So let's see what happens. Okay, so continuing on with our working out, we've got one integral that's very easy because it's the integral of a constant, and we've got another integral, which we've already said this is the same as the original. So there's a lot of information there. Let's break it all down. So first integral, let's actually work this out. And remember, guys, I called this integral I. So now I can just, don't worry about this. I can now say that I, which is what we're trying to find, is equal to this integral, which we're going to do right now. So this is the integral of the natural log of 2. So it's kind of boring because it's just going to be the natural log of 2 times u from 0 to pi over 4 minus this integral. But guys, we already worked out that this integral is the integral that we're trying to find as well. So you've probably seen a similar thing like this before, where you actually end up having an integral and then you later end up saying that it's equal to kind of itself in some way, or it's equal to something plus itself or something minus itself. And so actually we've now got this equation here, that the integral is equal to the natural log of 2 times u from 0 to pi over 4 minus the same integral. And just to be clear, it's because this integral is the same as this integral. Just because one of them has a u, one of them has a theta, it doesn't matter. They are the same thing because u and theta are just dummy variables. If you really, really, really want, you could just say, let u equal theta and just replace everything. And then you can say that it literally is like photographically identical, but mathematically they're already identical. So this is completely fine. Rearranging it, we then have that 2i, just by adding I to both sides, is equal to this bracket here. So this is going to be the natural log of 2 times pi over 4 minus 0. Okay, so just I is going to be equal to half of this. So the natural log of 2 times pi over 8, or I'd write it as pi over 8 times the natural log of 2. Okay, and that's the answer. So that's what this integral is equal to. The integral from 0 to 1 of the natural log of x plus 1 over x squared plus 1 is pi over 8 times the natural log of 2, which I think is a really cool answer. I always like it when there's a pi and something to do with like natural logs or e. I just think that's cool. So a really, really cool answer. And as promised, we are going to go even further as well, because I can also show you a way to look at a more general version of this. Okay, so let's not rub it fully out. I'm going to write it over here that I is equal to pi over 8 times the natural log of 2, because we actually will need this, I think, in a second. But I will rub all of this out, and I'm going to show you how to also generalize a slightly more, I would say, interesting looking integral. Okay, so we're going to start with the same one, but I'm just going to make a different substitution. Okay, and you're going to see what happens. But if you don't care about this, then, you know, go home. Doesn't matter. But I think this is really cool, so I'd recommend sticking around. So instead of just this integral on its own, I'm going to make a substitution. I'm going to say, let t equal ax, where a is just a positive constant. Okay, so a is just greater than 0. Okay, it's just some constant. Then I can rewrite my integral I as the following. So when x is 0, we can see that t will be 0. So this is still 0. But when x is 1, we've got an a up here. Hopefully that makes sense. Then we've got the natural log of, and then x is just going to be t over a. So t over a plus 1 divided by, and then we've got t over a squared plus 1. And dx, what's that going to be? Well, we can see that dt dx is a. So we can see, let's actually write it down. dt dx is just a. So that means that dt is a dx. So dx is dt over a. Okay, so let's do that. So this is dt over a. Okay. Now you might say, whoa, what's going on there? Well, let's see. So now we've got the integral from 0 to a of the natural log. And then, guys, this t over a plus 1, I'm going to rewrite this as t over a plus a over a. Okay, you'll see in a second. And then this here, we can simplify it to t squared over a squared plus 1. And also, I'm going to take this 1 over a to the outside of the integral. So I'm going to go 1 over a on the outside there, dt. Okay, so it's just a lot of simplifying and rearranging and, you know, all that good stuff as normal. Let's go up here. And then this is going to be equal to a times the integral from 0 to a of the natural log of, and then here I'm going to do t plus a all over a, so one big fraction, t plus a over a divided by, and then I'm also going to multiply the top and the bottom of the main fraction by a squared. So I'm going to get t squared plus a squared on the denominator, and I'm also going to get an extra a squared up here, and then I've got a dt there too. Also, I'm sorry, but I have made one mistake. I've put an a here, and it should be a 1 over a. So I'm sorry if that was confusing, guys. That should be a 1 over a. But the reason that I did that is because it ends up being an a, because you've got a squared over a. So it does end up being an a. And then I've got integral from 0 to a. That's already cancelled out. And then I've got the natural log of t plus a minus the natural log of a, all divided by t squared plus a squared dt, like that, okay? And then you're going to see something, I think, pretty cool. So this is equal to a times the integral from 0 to a of the natural log of t plus a over t squared plus a squared dt. And then I've got minus a, and I'm also going to take the natural log of a out, so the natural log of a times the integral from 0 to a of just 1 over t squared plus a squared, okay? So I've kind of done like several steps in one go. So I've split this into two fractions, and then I split it into two separate integrals. And then from the second one, I've got the a, so the a is still there, and I've also taken the natural log of a to the outside as well. That's what I've done in that step. Okay, cool. Now, we've said that this is still the integral I, okay? That's what we've still got. So this is still equal to I, okay? And now what you can see is we've kind of got a similar situation happening again. But first of all, let's look at what this is. So we've got that I is equal to a times, and then that's not exactly I. So that's just the integral from 0 to a of the natural log of t plus a over t squared plus a squared. We don't know what this is, but you might say, but isn't this I? The only difference between that integral and I is that this goes from 0 to a, and this goes from 0 to 1, so they're not the same. And also, oh no, and there's actually quite a lot of differences actually, because you've got a's all over the place. So I'm sorry, it's actually definitely not I, because it has lots of differences. This is the new one that we're looking for. And then here we can do something with this. So we've got minus a times the natural log of a. And now here I'm going to use a fairly well-known standard integral, which is that this integral here, okay, this integral is equal to 1 over a times inverse tan of x over a, and kind of, you know, plus c, because that's an indefinite integral, but we don't need it because we're doing a definite integral. So we've got a ln a times 1 over a times inverse tan of x over a, or t over a, in brackets, from 0 to a, like that. And then we can start evaluating. But guys, one thing I'm going to do now is I'm going to say that, remember, we worked out just earlier that I, which is the integral that we actually begun with, is pi over 8 times the natural log of 2. So now we can say that pi over 8 times the natural log of 2 is equal to a times the integral from 0 to a of the natural log of t plus a over t squared plus a squared dt. Now, this a and this 1 over a just immediately cancel out, so we can just, sort that out right away. And then we've got minus the natural log of a, and then here we've got in brackets inverse tan of a over a, which is inverse tan of 1, which is pi over 4, minus inverse tan of 0 over a, and that's inverse tan of 0, which is just 0. So just minus 0 there, okay? Cool, so now we're kind of getting somewhere because we actually know what everything is except the integral, but that's what we're looking for. So now, and I've just about got space, actually no I don't. Let's go back to the top. So we're back at the top, we can keep going. So we're just trying to work out what this middle integral is, so we just have to simplify everything. So if we get that on its own, let's add the natural log of a times pi over 4 to both sides. We have pi over 8 times the natural log of 2 plus pi over 4 times the natural log of a equals a times the integral from 0 to a of the natural log of t plus a over t squared plus a squared dt. Then we can just try and simplify the left-hand side. Let's also divide everything by a as well. So we've got pi over 8a times the natural log of 2 plus pi over 4a times the natural log of a is equal to this integral that we're looking for. Natural log of t plus a over t squared plus a squared dt. Lovely stuff. Okay, now let's give these two pi over 8a, pi over 4a, let's make them have, well, let's just make them the same number. How would we make pi over 8a and pi over 4a the same number? Maybe we can times the pi over 8a by 2, or maybe we can divide the pi over 4a by 2 and then times it by 2. That's what we're going to do. So this is what I'm saying. We've got pi over 8a times the natural log of 2. And then this term, I'm going to write it as pi over 8a. You might say, you can't do that. You just divided it by 2. So I'm going to add an extra 2 here. You'll see why in a second. And then this is still equal to the integral from 0 to a of the natural log of t plus a over t squared plus a squared dt. The reason why I've done this weird manipulation here is that I can bring the 2 as a power of a, so I can go that's a squared and then get rid of that. And then I can add the logarithms together because they have the same number in front of them. So now I have that pi over 8a times the natural log of 2 times a squared using another logarithm rule is equal to our integral, and we're done. Okay, so we basically have a better version of the Serret's integral that we were doing, because this is the integral that we were doing, and you can see that we've just worked out that the integral from 0 to a of the natural log of t plus a divided by t squared plus a squared dt actually has this very nice formula here. So I can also say, we know that this one was equal to pi over 8 times the natural log of 2, but now we know something even cooler. The integral from 0 to a of the natural log of x plus a over x squared plus a squared dx is equal to pi over 8a times the natural log of 2a squared. And actually, you can see that, for example, if you were to let a equal 1, because Serret's integral is just this integral, but when a is 1, if you do let a equal 1, you get pi over 8 times the natural log of 2, which is the same answer that we get to Serret's integral. So they really are the same, but this one is maybe even cooler because you can use any value. So you could have, instead of 1, the integral, of course, from 0 to 2 of the natural log of x plus 2 over x squared plus 2 squared if you want. And of course, that's just going to give you something different. So it's really cool that you can just basically choose any positive value of a and it just works. So yeah, that's the idea. And the coolest part about this is you kind of have to know what this is. So this integral is kind of like, it's almost very unique because this integral is kind of like a stepping stone for answering this one. So to answer this integral, you have to answer another integral that looks similar. So to get the more generalized form, you actually have to do a specific one, which I think is pretty cool. Anyway, guys, that's enough waffling. Thank you so much for watching. Please like, subscribe, share, do all of that stuff if you enjoyed the video and watched it to the end. I highly appreciate it. And yeah, I'll see you in the next one. Cheers.